Hello everyone. In this video, we are going to talk about comparison-based algorithms, as known as like decision trees. So the decision trees is like one of the main topics in algorithms. Also, like it's a foundation topic of like one of the foundation topics of artificial intelligence as well. So let's give an example. Let's start. So let's think about like three numbers, A1, A2, and A3, but just keep in mind that these numbers are not no duplicates in them, so they are not same, they're all unique. And let's say like let's compare them and like let's form some sort of a tree. So you start with actually comparing two numbers, right? A1 and A2. So if A1 is greater than A2, you form a branch, and if A2 is greater than A1, you form another branch. Basically, it's going to be like a binary tree. So as you see here, as I said, A1 is greater than A1 is less than A2 here. The other vice versa. A1 is greater than A2 here. And then for this one, now you're going to compare with, okay, you know that A1 is less than A2, but how about the relationship between A2 and A3? So now A2 is less than A3, A2 is greater than A3. So now you know that like this is greater than this one, and A3 is greater than A2. So it's like pretty straightforward. You're going to see an output very soon. This is the output because like it's nothing complicated. But for this one, A2 is greater than A1 and A2 is greater than A3, but it's not enough to come up with a solution yet. So you need to compare A1 with A3, and then you can decide like which one is actually the correct order. So for this one, the order is like A1, A3, A2. This one, A3, A1, A2. So this is like the left side of the tree. For the right side of the tree, it's going to be the same thing again. So now you have, let me remove myself from the screen. So now, as you see, you have like three numbers here with no duplicates. And then you ended up having six outputs, like 1, 2, 3, 4, 5, 6. This is basically a permutation of three, basically, like a single, like unique permutation. So, and to calculate that, basically, it's like 3's factorial. 3's factors, 3 times 2 times 1 is basically 6. That's why we have 6 outputs. And if the numbers are like, let's give an example, A1 was like 9, 4, A2 is 4, and A3 is 6. Basically, 9 is greater than 4. You select this branch, and then you compare 9 and 6. 9 is greater than 6, and now you compare with like 4 and 6. 4 is less than this, A3, 6, which is 6, and then you end up with like this output here. So this brings us to a valid statement that every comparison-based algorithm has a corresponding decision tree. So which means that we can form a decision tree based on the all like comparison and like sorting-based elements, sorting-based like algorithms. So different number of inputs, meaning you are going to end up with different tree, and which is like designated by the permutation of the number of the inputs. So here, every possible output must be represented by at least one leaf. So as you see, these are the outputs, and also within the tree, you call them leaf as well. So each leaf just is represented by an output. And every path from the root to leaf represents the execution. Basically, we did in like 9, 4, 6 example in the previous slide, the algorithm for the specific input. And the path length, like here, is giving us the time complexity, basically. So the longest path should be the worst case time complexity in this manner. So you can just like give the worst case scenario, the upper bound for like as the longest path for every comparison base and the decision trees. And which brings us to the sorting lower bound. So a lower bound for the worst case time complexity of all comparison based sorting algorithms. So which means that whatever sorting algorithm you have, if you're like comparing numbers, either like insertion sort, selection sort, heap sort, merge sort, doesn't matter, that we have some like tree, we can represent that by tree with a decision tree, and we can just like give them some lower bound for that sorting. So let's consider the decision tree like the best algorithm ever. Doesn't matter whatever it is, like number of inputs, and you have like the outputs, which is like the permutation. And as I said, so the number of leaves basically needs to be greater than, if I have like n elements, n items here, then I will have n factorial, at least n factorial leaves, like if there is no duplicates. So this brings us, okay, how like the number of the height basically here will be, so since this is like height, and the height should be some log base, log 2 base n factorial, because like there is like number of leaves, like n factorial of number of leaves. So how can we find a perfect approximation for upper bounds and lower bounds? So the worst case time complexity for is going to be greater than log base 2 n factorial. Okay, let's figure out how can we do the approximation of log base 2 of n factorial. So let's do it for upper bound first. For the upper bound, let's do an exaggeration here. Log n factorial. I have log n factorial. And log n factorial, if you remember from previous videos, like we said, like we have constants here, and then polynomials, sorry, logarithms, polynomials, exponentials, factorial, and in the end, like we had in the very beginning, like video, like n to the power of n, which is like huge. So we are saying no matter what, like my exaggeration will be log n factorial will be smaller than log n to the power n. So log n to the power n, as you see, is this exponential, just by the logarithm rules, it's going to be coming here, and it's going to create like n log n. So basically, you can say log n factorial is O n log n. How about the lower bound? For the lower bound, like some omega notation, and now we are just doing here like n factorial, n times, n minus 1 times, n minus 2 times, n minus 3, 3 times 2 times 1. So we just like basically, this is the factorial of n. So we'll be doing some mathematical trick here. So I'm saying, yes, there is like n elements here, and you just multiply by them. I'm saying, what if like n is even, it doesn't matter really, but like approximately, if n is even, can I write them in n over 2 items? There's like 10 items here, and I'm wondering if I can cut it into half and then make them n over 2 items, meaning I'll pair them. So let me pair them. So there is n here, there is 1 here, n times 1. There is n minus 1 here, there is 2 here. Let me pair these ones here. There is n minus 2 here, there is 3 here. Let me do it with this one. So when I just pair them up, basically there will be n over 2 pairs, right? And in the end, like the last pair would be n minus n over 2, n minus n over 2. So I'm coming with an approximation saying that this is roughly n times 1 is like basically n. So this one is n. This one is like n minus 1 times 2, basically like 2n minus 2, but we can like make an approximation and assume it's like still n. And this one, like same thing applies, n, and assume that like my approximation is just like this is n as well. So I will end up having n, but multiply by n over 2 times. So if it's only one n, n. Two n's, n squared. Three n's, n cubed. How about n over 2 of n's? N to the power of n over 2. Assuming that n is even. Otherwise, you would just like lower it and then use that form. So log n base n over 2 is basically, this is the exponential. So the exponential is going to be here, and log n factorial is greater than 1 over 2 n log n. So in the worst case scenario, you basically have, for all comparison-based sorting algorithms, you're going to have n log n here, and you're going to have 1 over 2 n log n here. So which means that in the worst case, the decision trees, the comparison-based sorting algorithms, will give you this lower bound with this approximation. There is also another approximation called Sterling's approximation. You can just Google it and find how it works. And thank you so much for watching this video.